All right, let's take a look at exercise number 3. This is one we didn't quite get to finish in class today. So with this problem, we're focusing on working through a couple of our equations. First one being the change in energy. And energy is a result of Q, which is heat, plus W, which is work. And the symbol for Q and W is dependent on whether the heat is entering our system or leaving it. So if it's entering it, we have a positive change in energy, so Q would be positive. And W is work, and if work is being done on our system, it also will be positive. Now work in this case is really in terms of volume. So we're going to be looking for something that if it's going to be positive, that we're going to have the volume changing and getting smaller compression. And W, if it's going to be positive, we're going to see expansion, okay? And we saw that in part of our notes too, as far as how to assign Q positive, Q negative, W positive, W negative, right? So that's our first equation. Our second equation is has to deal with work, and it is W equals the negative pressure times change in volume, okay? And the reason why this is a negative here, because if this is expanding, okay, that means that our volume is getting bigger, that we are actually, work is being done on the surroundings and not on the system. So that equates to a negative W because the expansion, right, is increasing the size of our object. All right. So here's our variables that we're going to be using. My suggestion is when we come up to a problem like this, is we write down our equations that we know, and then we read through the problems and we fill it in. Okay, so here we go. A balloon is being inflated to its full extent by heating the air inside it. Okay, so when this happens, we're assuming that those molecules are going to move faster, and we're going to have an increase in the size of our balloon. The final stage of this process, the volume of the balloon changes from 4 times 10 to the 6 to 4.5 times 10 to the 6. So we do see a change in the positive. Okay, so this is going to be where it's going to say that our W here is going to be negative by the addition of 1.3 times 10 to the 8th joules of energy. Okay, so here's our addition of energy. And this energy that's coming in is actually our Q. So Q is thermal energy, 1.3 times 10 to the 8th. And let's put our units on there because this is in joules. Very important that you do this because it's really easy to just put everything in kilojoules. We will see a lot of our questions done in kilojoules. However, this one is set up in joules. And it's perfectly okay to have a change in energy in joules. We just need to make sure that we're consistent on both ends of it. All right. So we do have Q, we don't have W, but we do have this change in volume. And then as this goes on, assuming the balloon expands against the constant pressure of 1 atm, so our P here equals 1.0 atm. And please don't shortchange the process. Put your units on your intermediate steps here, so you can give you a full view of this problem. So we need to know what this is to solve this equation, all right? But in order to get W, we're going to have to determine what delta V is, okay? So here's delta V. Quick review of deltas, final minus initial. And that is for always for anything that has a delta with it. And so we have our final volume is 4.5 e to the 6th. And you can write this in whatever format you want. I like using the e's because it's a little quicker. And this equals, when we punch this into your calculator, notice this has 3 sig figs, 1, 2, 3, 1, 2, 3. Our answer should also be in 3 sig figs, and it is 5.00 e to the 5th, okay, when we subtract them. All right, so now we do have our answer here for our volume, and this is in liters. Make sure we don't leave those without units. And now let's plug this into our work equation. So work equals negative P delta V. Okay, or that equals negative 1.00 ATMs. Is it 1.00? Let's check it. Oh, just 1.0. Okay, 2 sig figs on that one. 1.0 times 5.00E5, and this is ATMs, and this is liters. All right, and this will give us 5.00E to the 5th ATMs per liter. Now there's a slight problem with our answer at this point because the W that is a part of the E equation is actually in joules, okay, or kilojoules. This needs to be in joules. So we're going to need to convert this into joules, and there is a conversion factor. It's listed right here on our sheet, okay. And I want you to get used to these units, how they're written. Okay, 1 liter per atmosphere equals 101.3 joules. All right, so 5.00 E to the 5th atmospheres per liter, okay, times 101.3 joules is 1 ATM per liter. Okay, and they don't expect you to write these out. However, it's a really safe way to do these problems because we see that our units cancel out, giving us an answer with a unit we can deal with. Okay, so my recommendation when you do these is that you write out these units because you will see them canceling out. And this gives us a value of 5.065 E to the 7th joules. Now, notice that this has a negative right here, so this is actually a negative number, which makes sense because the work that is being done, we have the expansion of the balloon, so we're pushing that balloon into the environment. All right, last thing to do here, because this is our W, is to combine our Q and our W, so delta E will equal Q plus W, Q being 1.3 E to the 8th joules, and plus a negative 5.065 E to the 7th joules, and that gives us 7.935 E to the 7th joules, or if you feel more comfortable in kilojoules, divide that by 1,000. 7.9 E to the 7th kilojoules. This is probably the answer we prefer. I also noticed I put this in sig figs. If you wanted to put the joules one in sig figs, it would look like that. You could just round down to 3.5 because we have 2 sig figs. Where did the 2 sig figs come from? They came from, I think, our pressure. Our joules of energy is in 2 sig figs, as well as our pressure. Okay, so 2 things that will drive that to 7.9 being our answer. All right, there we go. There's our wrap up from class today. Bye-bye.